All right, folks, so we're going to spend some more time looking at Chapter 5.1. I know you folks already previewed it after our assessment last week, but after talking to many of you, it seems like spending a little more time on our exponent rules will really benefit you versus kind of brushing over it and then expecting that you already know it. So we're going to focus on those today. We're also going to talk about other polynomial functions using addition to combine them, subtraction, and multiplication. Now, before we get too much in depth, we're going to work with monomials right now, which are pieces that are made of numbers and variables that are just multiplied or divided by each other. Later in this flipped lesson, we're going to talk about polynomials. Now, polynomials means they have several pieces to the equation that are all added or subtracted to each other. So, for example, a monomial might be 2xy. It's one piece connected by multiplication or division. A linear equation, such as 1/2 x minus 3, this is a binomial because it's made of two pieces. If we think of certain quadratics, this is made of three pieces, so we call it a trinomial. Today, like I said, for this right now, we're going to talk about monomials because they're a little simpler. But when we do addition, subtraction, and multiplication, we're going to look at polynomials, which means they can be made of 1, 2, 3, 4, or 10 pieces. It doesn't matter. It just means many parts. So, let's hop back. Hopefully you have this note sheet you got from the sub. We're going to go over the definitions and examples for some of these exponent properties to make sure that you didn't just skim over them, that you actually spent some time thinking about using them and using them correctly. So first we have the product of powers property. And what this means is if we have some base, x, to the power a, times another number with the same base but with a different exponent, we can simplify this easily by taking our base and just adding our two powers. So for example, if we're going to use all numbers, get rid of the a's and the x's and the b's, if we have 3 to the second power times 3 to the fifth power, we could plug these into our calculator and solve it, right? 3 times 3 is 3 squared, or 3 times 3 times 3 times 3 times 3 would be 3 to the fifth. Or if we just want to simplify it out, save some time, it would be 3 to the seventh power. We would do our 2 plus our 5. And then we could plug that into the calculator. That's going to be even quicker. Okay? Again, we could do it with some sort of letter. We could have a to the fifth power times a to the 10th power. We're going to have a to the 15th power. Okay? So when we take two bases that are the same value, we multiply them together. All we have to do to combine them is to add our exponents. Next, we have a quotient of powers, and the quotient of powers has to do with division. So, for example, we have x to the a power over x to the b power. Again, there's an easy way to simplify this. If we look, we had multiplication, so we added. Here we have division, so we're going to subtract. We'll end up with x to the a minus b. It must always be the top minus the bottom number, okay? Subtraction, the order matters. With addition, it's not as important, but here we don't want to change our solution. So if we have 9 to the second power over 9 to the first power, which we could just write as 9, we would have 9 to the 2 minus 1, which is 9 to the first power. Okay? Let's do one without a 2 and a 1. Let's do 7 to the 15th power divided by 7 to the third power. That's the same thing as 7 to the 15 minus 3, which is going to be 12. Now, when we do this, there's times we could get negative exponents. So that's what I want to talk about now. Okay, when we do this subtraction, there is a possibility for a negative. And if you have a negative exponent, it's not in simplest form. You need to continue simplifying it, get rid of that negative exponent. And this is the way that you do it. So say, for example, you get x to the negative a. Okay? This negative exponent means that we need to change the location from this number being in the numerator, the top of a fraction. Essentially, its denominator would be 1. Okay? And we're going to flip it. We're going to move this whole chunk down below. We get rid of the negative sign because we've moved it. And then above it will be a 1. Now, you could have other letters here, but all it means is that the negative exponent, you push it to the bottom. Likewise, if you have a negative exponent in the bottom already, then that is equivalent to bringing it up and keeping our positive as negative, so x to the a power. We'll do an example of this now too. So let's say we have 3 to the negative second power. That is not as easy to figure out in your head. It's not going to be 3 times 3, which is 9, negative 9. That's not right, okay? This negative means we need to move it underneath into our denominator, and then we get rid of that power. So this, instead of being 9 or negative 9, which you might assume, is actually going to be equal to 1/9, okay? Where we flip it below, and then we take whatever that power is and solve that out. Let's do another one. Let's say we have 5 over 7 to the negative second power. We're sticking with the seconds because I can square quickly in my head, okay? This is the same thing as bring up this to our top. The 5 is already to the first power, which is positive, so we're going to leave it there. It's like 5 times 7 squared. Well, that's like 5 times 49. 5 times 9 is 45. 5 times 4 is 20, 24. So our answer here is going to be 245. Okay? So whether our exponent is connected to a number that's in our numerator, we move it to the denominator, or if it's in the denominator with a negative exponent, we move it up to the numerator and then do whatever we need to get to our solution. So negative exponents, we move them from the bottom to the top or the top to the bottom. When we're dividing, we subtract. When we're multiplying, we're going to add. Another situation is when you have a power to another power. So for example, if we had x to the a, which we've used a lot of times, and then we took that whole chunk and we raised that chunk to another power of a different number or the same, it doesn't really matter. The simplest way to do that, we already did addition and subtraction. Here we had some other stuff going on. We take these two powers and we're actually going to multiply them together. Okay, that's how we simplify a power of another power. So if we had, let's do 4 this time. Let's do 4 squared and then to the third. This can be simplified quickly, not to 4 to the 5th, which would be if they had the same bases and being multiplied, but 4 to the 6th power. Say we had 5 squared, and then that was raised to the third, and then that was raised to the 10th, okay? We can simplify that really quickly. It looks complicated right now, but any power to another power means that we're going to multiply all of those exponents together. So we're going to have 2 times 3, which is 6, times 10, which is 60. 5 to the 60th power. So again, when we have an exponent to another exponent, we multiply. Next, we have power of a product, which means we're going to have a couple letters. We'll do x and y. They're obviously being multiplied together, hence the word product. And we're going to raise that whole chunk to the power of a. This is somewhat like the distributive property. We're going to send that a to each of these two parts, okay? But we're going to use this idea here. If this is to the 1 and this is to the 1, we're going to send that a to here by multiplying by whatever exponent is already there. So x to the 1 times a, which is a. And the y, which is to the first, we multiply by a, so it's 1 times a, which is a. We distribute that through. Now, if there's other powers here, which we'll do in our example, you'll see that does change it a little bit. It's not just going to be obviously a copy of whatever that is on the outside. So let's say we have y to the 5th power and m to the 3rd power, and we're going to raise it all to the 2nd. And I ask you to simplify that. You're going to send this second to each of them. When we have a power in another power, we multiply, okay? Power to a power. So here, this is going to not be y to the 5th anymore, it's going to be y to the 10th. This isn't going to be m to the 3rd anymore, it's going to be m to the 3 times 2, which is 6. Okay? We just take this rule here, and essentially we're distributing it to each chunk. Next, we have power of a quotient, which works almost exactly like the power of a product. We have some division problem with an a, okay? And again, we're just going to distribute this to each chunk. So it's going to become x to the a power over y to the a power. Again, each of these are 1, and that's why it ended up that way, okay? We send it to each chunk. Now, you could be distributing an exponent that is a non-positive, okay? So, for example, it could be a negative a. We might have x over y to the negative a. We're still going to send that negative to each piece. So you would have x to the negative a, y to the negative a. But earlier when we did this, we said negative exponents you should not have. So we're going to move this below and this above, in order to cancel out our negatives. So we're going to end up with y to the a power over x to the a power. Do a few of these examples. You're going to see this very often, okay, where we have to distribute that across both a numerator and a denominator. So this property you're going to use pretty regularly. Let's do, let's do 3x over r to the third power, okay? So what we're going to do here, just like we did here, we're going to send this exponent to each piece. We don't just send it to the x and the r, which is I'm sure what you were thinking automatically. You also have to send it to any constant, okay, to every single piece that is being multiplied there. So we're going to have 3 to the third, x to the third, over r to the third. And again, it's only the third because each of these were ones. Let's say for a second, and maybe I should have set it up this way initially, let's change this r to the power of 4. If I do that, then 3 times 4 is going to be 12 down there. Okay? Now this can be simplified more. 3 to the third is 3 times 3, which is 9, times 3 again, which is 27. So we're left with 27, x to the third over r to the 12th. And again, it's 12 because I changed that to a 4 to kind of show you, especially in your notes, that if there's a different exponent, you need to multiply those two together to get the product. The last rule or the last property we're going to look at is really the easiest. It's called the zero property. Any number of any base to the 0 power is going to equal 1. Okay? And the reason why this works is a little complicated. I'll try to give you somewhat of an example or an explanation right now using our other properties to prove it. This isn't a real super detailed proof, but I want you to see why that comes about. Say we have x squared. X squared is x times x. I'm sure you and I and everyone that does anything about math can agree with this statement, okay? If we want to get x to the 0 power, I could take it and divide by 2, so that when I subtract them, I get 0. So I'm going to divide by x to the second power, which means I'm dividing by x times x. Okay? Here, if I do that, through the quotient of powers, I see that I'm going to subtract those. So I'm going to have x, 2 minus 2 is 0. Now here, this cancels and this cancels, but when things cancel, they don't become 0 all the time. This is a division problem. X divided by x. Well, that solution is just 1. Whenever your numerator and denominator are the same, that simplifies to 1. So x squared over x squared equals 1. Okay. You probably don't like that reason. If you don't like that proof of it using our quotient property, then you're just going to have to accept it as one of our math laws that you might not like but need to know. So this is a lot. Okay, none of these rules are especially hard, but it's very easy to make some mistakes. So don't lose this note sheet. Okay, it has a lot of good information on it for you. Next, I want to take a look at a couple examples on the very bottom of this. I think there's 4 of them. So we're going to do those together and then move into addition and subtraction of polynomials. All right, so let's do a couple examples now that are going to use most of, if not all of these properties from above. Okay, so there are 4 outlined at the bottom of your sheet. We're going to do 1A, 1B, 1C, and 1D. So here we see that we are multiplying 2 monomials again. They're monomials because they're one piece. They're not separated by addition and subtraction, so they're not a polynomial. They're just a monomial, one chunk of things squished together. So we're going to take these 1 pieces and we're going to start using some of our properties. We know this chunk is being multiplied by this, so we're going to kind of combine like terms, but it's not really combining like terms. It's just doing the multiplication with the pieces that make the most sense first. So if we have this chunk times this, I'm going to take my constants right now, and I'm going to multiply those. 2 times -7 gives me a -14. Again, I'm simplifying these, so I'm probably not going to get to like a strict answer with it, but I'm going to still have variables with simplified powers and numbers that I don't have to multiply together anymore because they've already been multiplied. These 2 are done. I got my -14. Next, I'm going to look at my x's. I have x to the third times x to the fifth. So this is our product of powers property, which means I'm multiplying the 2 bases, so I add my exponents.
Please pardon this interruption. TJ Morrow, your question and answer period has come and gone. Time to return back to the library. Thank you.
All right. So the result of that is x to the 8 if I do 3 plus 5. Okay. I'm done with the x's. Now I'm going to move to my last chunk, which is the y's. Now here I have y to the third times y to the negative sixth. Again, this is my product of powers, which means I add these. Now, because one's negative, obviously I'm subtracting, so I'm going to get to the negative 3. Now, right now, you might think this is all well and good and it's done, but it's not. You can never have exponents that are negative and call it simplified. They must be moved around and brought to where they belong. Because of our negative exponent property, that states that whatever it's attached to should be moved into the denominator if it's in the numerator, or vice versa, and the power becomes positive. So we're going to have negative 14x to the 8, all in the numerator. Those aren't moving, okay? This number can be negative or positive. It doesn't matter. It's all about the exponent. And then this, because it has a negative exponent, is going to be moved into the denominator. This is our solution, or our simplified version of this problem. Let's move over to 1b. We can tell here, definitely, that this is going to be a power of a quotient, okay? Excuse me, not power of a quotient. A quotient of powers problem. If you don't remember the names, personally, it's not a big deal to me, but you should know what it means, okay? Here, we'll start off with the c's, okay? In our quotient of powers, we found that we can do top to subtract the bottom when we have a division problem. So c to the 5th power divided by c to the 2nd power simplifies to c to the 3rd power. So that's what I'm going to write as that simplified. I'm going to look at my d's. I have d to the 3rd and d to the 7th, so I must do 3 minus 7. So I'm going to have d to the negative 4th. And then I'm going to have this, but this should still be simplified. 15 divided by 3, or excuse me, negative 3, is going to be negative 5. Okay? So I take care of my constants. I take care of each variable in line with each other by subtracting. Now, again, this is not entirely simplified. I have a negative exponent I need to take care of. So I'm going to still have a negative 5 and a c to the 3rd power in my numerator, but this, because it has a negative power, must be moved into my bottom, and the power must be made positive. Okay, so we have negative 5c to the 3rd divided by d to the 4th. So when we multiply our powers, we add them. When we're dividing bases that have the same powers, we subtract them. Here, we're going to distribute this power to each chunk. So we're going to be left with a to the negative 3 over 4 to the negative 3. Now this we can simplify. There's no letters there, okay? It's just numbers, so we're going to have to figure out what that is. And then we have a negative exponent up here also. I'm going to start by moving things around. I'm going to take this a to the negative 3 and move it into the denominator and make my power positive. I cannot simplify that anymore. Now, because this has a negative exponent also, I'm going to take that and move it into its opposite location, which would be the numerator. So I'm going to have 4 to the 3rd power. Whether you want to or not, you can solve 4 to the 3rd power. It is 4 times 4 times 4, or 16 times 4. 16 times 4 is 64, okay? So this simplifies to 64 over a to the 3rd. At this point, I have no numbers I can multiply or divide by. I have no repeat letters and no negative exponents, so I am at my solution right there. Lastly, we're going to distribute this 5 across all of these pieces, okay? Remembering now, here they each had a power of 1. We're going to have to do a little bit of additional work as we send it to the x cubed and the y squared. So our first piece is going to be negative 2. Its exponent was 1 times 5, which is 5. Okay. We have x to the 3rd, which we're going to multiply by 5, so we're going to have x to the 15th. And the y squared times 5 is going to be y to the 10th. We have no negative exponent, so there's going to be no denominator here except for 1. But I can simplify this. Now remember, this negative 2 to the 5th means negative 2 times negative 2 times negative 2, and so on. Oops. And so forth. Okay? 5 times. Negative 2 times negative 2, positive 4, times negative 2 is a negative 8, times negative 2 is positive 16, times negative 2 is a negative 32. So you have to be careful with that positive negative sign, okay? You need to make sure you don't lose it and you maintain it all the way through. If it's an odd power, your answer is going to stay odd. If it's an even power, then the odds will cancel, the negative signs will cancel out and you'll end up with a number that's positive. So here, instead of negative 2 to the 5th, I'm going to put negative 32, x to the 15th, y to the 10th, and now I have simplified this equation out. You're going to see there's a lot more complicated things that you can solve with these, or at least simplify down from some really big nasty looking thing, combine all your letters together, and you're going to end up with something that might be a one sentence or a simplified quotient problem. Okay. Now we're going to take a break from our monomials, which is one chunk pieces, okay? And we're going to start looking at polynomials, where we have maybe an x squared and an x and some sort of constant all being added or subtracted to each other. So go down to the next section, which says adding and subtracting polynomials. All right, let's take a look at how to add and subtract polynomials. Now again, polynomials, if you look here, this is a trinomial and this is a trinomial. It's a trinomial because it's made of 3 distinct parts, all separated by plus or minus signs. Over here on this example, we have 2 binomials. Each piece has only 2 parts. You can add a binomial to a trinomial and a monomial to something that has 4 parts. All of these are possible with addition and subtraction, but we're going to start by looking at a trinomial and we're going to look at binomials. So this is the first example of subtraction on your sheet. And this is what I think is a little bit harder than addition, so it's nice to get it out of the way. Now with this problem, we're really just going to combine like terms. The only dilemma is that with this negative sign here, or this subtraction symbol, we need to actually distribute it to each chunk. If not, you're only really going to subtract this first piece. So the way that I solve these quickly and easily is I just change all the signs. So this becomes negative 2x squared. Negative 1 times a positive 3 is a minus 3x. And a negative times a negative 1 is going to be a positive 1. Now at this point, I'm just going to combine my like terms. And by like terms, I mean the x's can't be combined unless it's an x squared with an x squared. Okay, your bases have to be the same. So if I look here, I have 4x squared. Excuse me, I should not include that negative sign. That's going to be with our x. 4x squared minus 2x squared. So I'm going to end up with 2x squared. Next, I'm going to look at my next terms. I have a minus, again, from attached to the 5, a minus 5x and a minus 3x. Together, I have a negative 8x. Again, I need to remember that I have to distribute that negative. If not, I would have ended up with a negative 2x here. Okay, so you have to be careful. Lastly, I have a positive 6 plus 1, which gives me a positive 7. If I did positive 6 minus negative 1, it's the same thing, but it's less signs to worry about if I just switch them all over as my first step. This right here is my solution to the difference, okay? It's kind of like when we added and subtracted complex numbers, you combine the pieces that are the similar base, okay? If it has an I, you combine the i's. If it's the whole number, you combine the whole number. Similarly with this, okay? Let's look over here. This is an addition problem. This is actually the 4th problem on your sheet. We're not going to do the other 2 together. I do want you to do them on your own. In order for you to get credit for doing these notes, you need to do it on your own. So if you want to watch this one, pause the video and do the other 2 problems. So here, for this one, addition is even easier. We don't need to distribute a plus sign because a positive times a negative is going to be a negative. And a positive times a positive, well, that remains positive. So it's really, the only challenge is remembering that this negative has to get sent to each piece. Here, we're going to combine like terms similarly, but in this example specifically, there's not a lot of copycats. For example, here we had a squared and a squared. Well, here we have no x squared to combine with over here, so we're just going to maintain it. We're going to keep our 3x squared. Next, we're going to go to our second degree, which is our first power, okay? Here we have an x. There's no x over here, so I'm just going to maintain this, negative x. If I could add it to an x over here, I would, but there's nothing else to add it to, so I'm just going to keep it. Lastly, I have a minus 6 and a plus 1. Well, those two, negative 6 plus 1 is a negative 5. This is my solution. Your polynomial should be in what we call a standard format or a standard notation, with your highest degree being first and going down in the correct order, okay? These were already outlined for you that way, but if for some reason as you're doing these, this gets all mismatched, and you have your first power in front of your second, or you have a third power at the end, you need to make sure that in your solution you put it into that standard form, which is your first piece must have the highest power, okay, or it must be to the highest degree. So pause this video, seriously, pause it, do. I think it's, I don't know, a couple other problems on it. I don't know what they're labeled, but there's one more addition and one more subtraction. So get those two done, and then we'll go over how to multiply polynomials. You folks already have an idea of how to multiply polynomials, but all you've really done is multiplied a binomial by another binomial, okay? And the way that we do this multiplication is by using FOIL, our first, outside, inside, last. So we do x squared. Our outside is x times a positive 3, so plus 3x, minus 2x, minus 6, and then we combine our like terms. Okay, and we get our equation. Foiling is all well and good, but it only works when you have binomials. We're going to kind of move it up a notch, okay? When we multiply polynomials, we could have something that is 2 parts, a binomial, but we can multiply that by a trinomial or something that has 4 parts, or we could do a trinomial times a trinomial. There's lots of possibilities, but we use the same idea of FOIL, kind of distributing things across to find our solutions to these, okay? We don't just multiply like pieces like you would think we do because of addition and subtraction. Let's take this idea of FOIL and we're going to kind of put it on steroids. We're going to take our first chunk here, being that this is obviously in 3 pieces, and we're going to send this first chunk to this whole piece over here. And you folks had one of these examples on your note sheet from after your test, but I know there was, again, a lot of confusion. So bear with me now. We're going to do this in chunks, okay? We're going to take this first piece, n squared, and we're going to send it to the second piece, our whole second polynomial, okay? We're going to take that, and we're going to add to it our second piece times this whole chunk here. And then we have a third piece, and we're going to send that to our binomial again, okay? So now we have this really long string of little equations here. When this is right next to the equal sign, it means, not equal sign, parentheses, it means we're going to need to distribute it to each chunk, including the sign in front. So this won't just be 6, it'll be a negative 6 being sent to each piece. So n squared times n is going to be n times n times n, or n to the third, plus 2 times n squared, which is 2n squared. Now we're going to have a positive 4n times n, which is going to be a positive 4n squared. Positive 4n also times a positive 2, plus 8n. Here we have a negative 6 times n, minus 6n, and a negative 6 times a positive 2, which gives us a negative 12. Just like with FOIL, we now are going to combine our like terms. We have n to the third, we have these two, which is going to be 2n plus 4n, 6n squared. Sorry, they're all squared. Here, these two are of the same base, so we're going to have an 8n minus 6n, which is a positive 2n, and then a minus 12. This right here, again, my highest exponent is first, going down in order, is the solution to multiplying these two polynomials together. Now, if you look at this chunk right here, this piece, and what it ends up equaling is kind of like FOIL, okay? We're going to send this to this piece, and we send the same to this. So n squared times n to the third. N squared times 2, 2n squared. We take this, and we send this to each piece also, okay? We just wrote it a different way down here. 4n times n, which is n squared, 4n times 2, which is 8n. And then lastly, we do the same with our negative 6. So you can see we actually take each piece here and multiply it double to each chunk here, okay? That's how FOIL works, folks. Instead of having a nice little acronym for it, you just need to know that each piece must be multiplied by every other piece on the other side. And you can do it by taking your first and sending arrows to each chunk in the second. Both of the other examples on the sheet you have are a trinomial times a binomial. So I want you to take your time and try your best. Pause it if you want to. I'm going to do the next one right after this one, but I want you to give it some effort first and check and make sure if you did it correctly. However, the third one I'm going to leave for you to complete on your own time. So, pause it if you want to. I'm going to erase this off and put up the next problem. So, our next problem's right here. We have x squared plus 4x plus 16 times x minus 4. Again, this is a trinomial because it's 3 parts, and this is a binomial. So, we're multiplying the two together. Now, instead of kind of taking this chunk and putting this parentheses next to it, I kind of want to show you how I'm going to fan it out and do it that way, okay? Because some of you may not really enjoy rewriting all of those steps otherwise. So instead, I'm going to do this, x squared times x. Well, x squared times x is x to the third. Now I'm going to do x squared times negative 4. So negative 4x squared, right? X squared times negative 4. Now I'm done with this piece. I'm going to go to my second one. I've sent this to each of those. I'm ready to move on. I have positive 4x. I'm going to send it to x. So 4x times x is a positive 4x squared. Now I have to send this chunk also to this piece. 4x times negative 4. So 4 times negative 4 is negative 16x. I have no other pieces to send this to, so now I'm done. I'm going to go to my third chunk, and I'm going to send this to my first piece. 16 times x is a 16x, and 16 times negative 4 is a negative, I feel like I just did this, 64. Now I can combine like terms a little bit quicker. Okay, I don't have to actually distribute. I just distributed everything to each of these pieces. There's no other cubes, so I'm set there. Here I have this chunk plus this chunk. I'm not doing anything with the powers, folks. I'm just combining like terms. Negative 4x plus 4x, that is 0 x squareds. So those actually canceled. It's okay if things cancel, okay? The squareds are not going to exist. In fact, if we look here, we have negative 16x plus 16x. Well, that's 0 x's. So that canceled also. And here we have a minus 64. Okay? This ends up being the solution to our multiplication of polynomials here. Things can cancel. That is fine if it happens. Okay? So try that third one on your own. See how you do. And then when you're done, there is a homework assignment at the bottom. It's in the ebook right there, 16 through 23, and 28 through 33, page 307. The first chunk is all simplifying like we did in the first half of the video. The second chunk is adding, subtracting, and multiplying. So take your time. There's not too many of that second piece, all right? I think there's 6 or 7. So do your best on it. And I will be in school tomorrow. I will also be after school today. I'm just in a meeting. So if you want help, you can come and see me at the end of the day or come in early tomorrow or whenever. You know I'm always here. If not, we'll go over all these answers in class when I see you next, okay? So do your best. Get that ebook work done. If you're struggling with it, come see me. Thanks, folks.